All right, welcome back. Today, I'm over here in Desmos, and I want to talk to us today about absolute value functions. So let's get started on that. So a couple of things about absolute value that we know of. We remember the number line, right? That the absolute value of a number is its distance from zero. So if I'm looking, for example, at the absolute value of 1, the absolute value of 1 is 1. And if I look at the absolute value of negative 1, well, that's also going to be 1. So negative 1, 1, 1, 1. So having said that, the parent function of an absolute value function is f of x equal absolute value of x. So let's get that into our Desmos, and then we'll go from there. So f of x, I'm just going to call it y for now, f of x equal absolute value of x. All right, so what do we notice first about the absolute value function, that parent function? First of all, it looks like a V, right? So the graph of the absolute value of f of x, it gives the distance from the line for each value of x. So we started absolute value of 0, 0, right? That stands to reason. The absolute value of negative 1 is 1. The absolute value of 1 is 1. So that's why you see that. So one of the couple of things is that the graph of that absolute value function in two variables is going to be V-shaped. So if you see a V-shaped graph, you know that's an absolute value function. And it's also going to be symmetric about a vertical line. Now, see that line right now in the case of the parent function, we know that this is the axis of symmetry. The axis of symmetry is going to be that line that divides it exactly in half, okay? That's called the axis of symmetry. Now, it's at 0, meaning it's the y-axis up and down, only because right now we have the parent function. So let's take a look at a couple of things about what happens with that parent function once we sort of start moving it around or translating it, right? So, and before we do that, let's talk about the origin here, or in the absolute value function, that is called the vertex. So we have the axis of symmetry that is exactly half, right? So this one starts at 0, and then exactly half of it goes the other way. All right, so let's start looking to see how the absolute value of this graph translates once we begin looking closer at the absolute value function. So I'm going to take the next one and I'm going to subtract 4 from it, and let's see what it does to our graph. So we're going to have y equal the absolute value of x minus 4. So what did it do? It took it from the origin, or again, the vertex, and it moved the vertex down 4. So you can imagine that using from the parent function, if I added 4, it's going to move it up to 4, right? That vertex is going to be moved up to 4. So let's test that out and see. All right, so we've got y equal the absolute value of x plus 4. And there it is. So it moved our vertex up 4. So now we've seen how it translates up and down the axis. And this is on its vertex. So what can happen then if we want to transform that function? So first of all, before that, we can notice something, is that translation did not affect the axis of symmetry. It didn't change at all. The width of the function didn't change at all. So let's look to see what happens from the parent function to cause a horizontal translation. So to get a horizontal translation, I'm going to have that parent function y equal, and I want you to play around when you get a chance on absolute value of x minus 4. So what happened there? When I said minus 4, it brought me over 4 from that vertex. It moved to the right 4 times. So to move to the left, I'm going to do what? I'm going to add 4, and that's going to translate my absolute value function over to the left, 4. So really good stuff here. Now, let's start again at the parent function, and let's look at how we can stretch or compress this. So if I want to stretch it out, then I'm going to have an a value greater than 1. And I'll show you how that, where the a value sits. So y equal 2 absolute value of x. All right, so I kept it there at the vertex just to see what would happen to it. So what happened to it? I gave it a value of 2, so anything greater than 1, and it squeezed it a little bit. So if I change that to 3, okay, see what's happening to it? 4, 5, etc. So that's vertical stretch and compression. So that gave us a vertical stretch and compression, or a vertical compression. So it kind of squeezed it out. So if we stretch it out, we can say anything y equal a absolute value of x, and we can stretch it out. So now then, let's look at how we can reflect that on the axis. So if we want a reflection, we're going to have y equal the negative absolute value of x. And so what that did is it gave us a reflection along that axis. Again, the vertex is reflected. All right, so we have a vertical translation, horizontal translation, vertical stretch and compression, and reflection. So what if I asked you a question here, and without graphing it, you took a look at 4 graphs and you answered the question, which one of these is the graph of y equal absolute value of x plus 2 plus 3? Which one do you think is that one? So let's graph it and see. Y equal absolute value of x plus 2. All right, we've got a little bit of, so our vertex is at negative 2. And then now I'm going to add 3 to it. All right, so you see how it moved that up along the y-axis so the vertex, this tells you about the vertex, and then the plus 3 tells you about movement up and down the line. So you would pick the graph then that has a vertex at negative 2, 3. And that would be the picture of the graph that you would choose. So what happened there is you have your absolute value function that gave it its movement to the left, right? It moved it from the vertex of 0, our parent function. And I'll highlight our parent function there, see what happened to it. Moved it to the left. Now, when I added 3, we kept that, except we just moved it up 3. So we have a sort of a combination. We went to the left and up, to the left 2, and then up 3. See that? To the left 2, up 3. So if you look at compression, vertical stretch and compression, let's take a look at one here. So we've got y equal 1/2 the absolute value of x. All right, so what happened there? We have a really wide graph. So that graph is so what you notice there is that it gave us, we're still at the vertex of 0, but it gave us a pretty large, it kind of stretched out. So what can happen to compress? Well, you can, let's see, if that says y equal 1/2 absolute value of x, what if we say y equal 2 absolute value of x? All right, so as we kind of grow, we compress. We made it smaller. So we went from 1/2, which was really wide, and then we gave it a compression of 2. So from that 2, see that right there, over to our compression here. So that stretch or what's called the stretch or compression factor is absolute value of A. And the axis of symmetry of that line is going to be our x value. So here's what I'm saying. If we have this equation, y equal a absolute value of x minus h plus k, here's what each of those are. That stretch or compression factor, that's going to be the absolute value of a. The vertex then is that going to be at h comma k, right? H comma k. So your h value, k value. That's going to be, and the axis of symmetry is going to be your h line. It's going to be the one that goes up and down. So that's how you can look at the equation or the general form of what's called the absolute value function, which this is the general form, and you can take a look at it like we used to with y equals mx plus b, right? We know that b is the y-intercept and was the slope. So that's the same thing over here. You can look at the stretch or compression factor, that's the absolute value of a. You can look at the vertex, and that's the point at h comma k, that's your vertex. And the axis of symmetry is x equal h. So x equal h on your value there of your absolute value function. So using that absolute value function in general form, y equal a, absolute value x minus h plus k, you can graph. So on some of these, you can do both writing an absolute value function or you can graph it. We're going to come back and write an absolute value function. All right, so we know that the graph of a absolute value equation looks like a V. And we looked at graphing and the changes in the graph, the transformations that is, in the graph based on the standard form of an equation. Now let's see if we can identify transformations based on the equation. So we're going to look at the general form of an absolute value equation. All right, so absolute value equation is y equal, remember, a x minus h plus k. And each of these has a meaning as we discussed earlier. So now let's take a look at an equation and see what changes or what transformations are occurring here, right? So here's our equation. Y equal 3 absolute value x minus 2 plus 4. So if we compare that to the general form of the absolute value equation, okay, in our general form, a equal 3 in our equation, right? Also, h equal 2. And finally, k equal 4. So what do we know about the vertex? Well, we know that the vertex is at 2, 4, right? 2, 4. So we got a vertex at 2, 4. What else do we know? Axis of symmetry. Our axis of symmetry is at x equal what? 2. All right, so we've got our h comma k, which is our vertex, And then we've got our axis of symmetry at x equal 2 right here. Now, what can we do to check it? Well, let's graph both of them. Let's graph that equation and see how it's transformed from the parent function. All right, so here's our parent function. We've got y equal absolute value of x. Now, let's look to see what our transformation is on y equal 3, absolute value x minus 2 plus 4. So y equal 3, absolute value x minus 2, and then we have plus 4. All right, so we can see the transformation there. We've got a vertex at 2, 4, and we got an axis of symmetry at x equal 2. So we were correct in identifying what we said was the transformation that occurred here, and we were able to do that by simply looking at the general form or the standard form of the absolute value equation and comparing that to our new one. All right, let's then, since we know how to graph them and we know how to identify the different component pieces of the general form of an absolute value equation, y equals a, absolute value x minus h, absolute value plus k. Now what I want to do is take a graph, and we want to do 3 steps to write an absolute value function. So step number 1 here is we wanted to identify the vertex of this absolute value graph. All right, so the vertex is at -1, 4. So -1, 4. Because that vertex is at -1, then I've got an h value that I know, so h equal -1. And what about my k value? My k value is 4. All right, so we already know 2 of these, h and k. Now, step number 2, since we have h and k, now let's turn our attention to a. We want to identify a here. So the slope, let's look at the branch to the right of our absolute value equation. And let's see if we can identify the slope. We can do rise over run. We can go down 1, so that's going to be negative 1, 2, 3. So -1/3. So I've identified it as -1/3 on using rise over run from the vertex. 1, 1, 2, 3. So because I went down, that's negative. So what is my a value then? My a value equal -1/3. So now all I've got to do is substitute those values to get my equation. So we're going to substitute the values of a, h, and k into my general form of the absolute value equation. So I've got y equal -1/3, that's my correct, that's my a value, and then absolute value x plus 1, right, that's my h value, plus my last value, which is 4, that's my k value. All right, so we took an absolute value graph and we created a function for it.